Okay, with that, we can continue. This is one of the best frameworks for doing few-shot learning. And the idea is as simple as, or if not simpler than what we just covered. And I like simple ideas that work in practice. This is the entire field of deep learning. Simple ideas that give you very good results. They're practical. Let's see what we have. What is the definition of few-shot learning or few-shot classification? First of all, this is different from the type of few-shot learning that we did when we were doing language and GPT models. For that one, you had a pre-training stage. And then because of the nature of the language, you could describe new scenarios in a human language narrative, and then you could condition on that narrative. This is different slightly. What is the definition here? This is about labels when it comes to classification. You are designing a classifier that you wanted to adapt to new classes, which you didn't see during training. And you want that adaptation to happen using very few examples per each class. These are new users of your new products on your website, therefore new classes. Don't worry about this part of the figure, about zero-shot learning. And if I forget to cover that, let me know, because I might forget. But we are going to be covering the few-shot part for now. And if you look at this figure and it is reminding you of clustering, you are not far off in your guess. It's going to end up being related. It's different, but related. And whenever it comes to few-shot learning, you are going to start with the inference part. Actually, whenever you're designing a product based on machine learning or deep learning, you're going to start with thinking about your end product. What is going to happen? What type of model you're going to be using when it comes to production time or inference time. Like before, you have a small support set of n labeled examples. These are new users, new products on your website. These could be images, they could be text, they could be speech, they could be tabular data, they could be social networks. So you have the flexibility to work with different types of data. And let's say this is just a vector. If it's an image, flatten it for now, just for the sake of the math. These are your input. For your output, you have K classes. These are the corresponding labels. And these are labels only at production time. These are new labels. And then you can start dividing this set, your support set, into smaller chunks. And what are those chunks? You pick a class, and then you look at all of the images that correspond to that class. Perhaps you pick a dog or pick the class of dog, and then you look at all of the images in your support set corresponding to dog, all of the dog's images, all of the cat images, etc. And this is a way of, it's a way for you to chunk that as the support set. You're going to define a prototype, and you can think of these as cluster centers. And if you were doing k-means, what would you do? You would look at the set as k, and then you would average those features to give you ck. And this is exactly these arrows that you see. This is the images of all of the dogs. These are the images of all of the cats. These are images of the airplanes. You featureize them, and then you add them up, or you average them. How do you featureize them? You're going to use a deep neural network. And this is why now you can handle different types of data. If you have images, perhaps CNNs or vision transformers. If you have text, work with transformers. If you have speech, you have CNNs, transformers, different architectures. If you have a graph here, a social network, the same thing. This is going to give you a neural network. These are going to give you some vectors, and then you can add up the vectors within that SK. These are all of the images of featureized dogs, or these are featureized images of dogs. Featureized images of cats is going to give you another C. So you have C1, C2, C3 in that case. And if you're doing one-shot learning, you have one example per each class. So this is just, there is no averaging going on. You just take that class, you just take one image. This summation is only over one image. Okay, perfect. Now you need to write down your probability. This notation is a little bit sloppy because you are conditioning on S. That's important. It's not only the image that you're considering, it's also the support set. And then what you do, you take an image, featureize it, or embed it. It's going to give you a vector. You compare that vector to these centers. And how do you compare? Perhaps you can look at the distance between the two, Euclidean distance. And because it's a distance, it's not a score, you need a minus sign here. Unlike cosine similarity, which is a score, here you need a minus sign here because it's a distance. And then you do your softmax. Okay, perfect. This is just a distance function. And then you do your training. How do you do your training? You mimic the setup in your inference. To do inference, you need to have a support set. You need to have an input image, and then that's it. But during training, not only you need a support set, you need to have an input image, you need to know the corresponding label because you want to maximize your likelihood. Okay, perfect. Let's see this algorithm for training, and let me break it apart. You have a training set. These are all of the images in your data set. Perhaps this is the entire ImageNet data. You have 1,000 classes, and for each class, you have approximately 1,000 images. Pick one of those classes and look at all of the corresponding images. That's going to give you decay. These are the images of dogs. These are the images of cats. K is counting dog, cat, etc. Okay, now you need to write down your loss function. You go ahead, out of those 1,000 classes, pick perhaps 5 of them or 4 of them. That's going to give you a set. Within that set, NC is the 5 classes that we picked. You are going to look at each one of those examples one at a time. Let's look at the dogs. You look at the class of dogs, and then you sample a handful of images. This is your Futile Learning. You sample 2 images, 5 images. From the rest of the images, you're going to sample your mini batch. Okay? So Q is going to give you your mini batch. S is going to give you your support. You create your C. These are these centers. Take your images, featureize them, compute your centers. Now that you have your centers, you can write down your loss function. How would you do it? Again, you go class by class. You picked 5 classes, and then you look at your loss function. This is basically you're taking a log of this probability. If you take a log is going to cancel the exponential. You're trying to minimize, therefore you're multiplying by a minus sign. You get rid of this minus, and then you're going to end up with D here. That's a term that goes here. And then the rest of them go in the denominator, or the denominator terms go in the rest of the terms here. And then you write down your loss function, you can optimize. Is this clear so far? Okay, awesome. Now we were approaching it from the clustering perspective. These are the centers of some clusters. Let's approach it from a classification perspective. Is it related to the type of classification that we are used to? The answer is yes. Let's look at this distance and let's expand it. This is basically the term that is going inside here. This is your D. Let's expand it. Now that you expanded it, the first term here, it goes in the exponential. It doesn't depend on C. The summation here is over K's. It is basically the summation over your C's. This term is exponential of that term. The exponential of the same term is inside all of the terms in this summation. You can take it out, and then you cancel it with the numerator. So the same term is showing up in the numerator and the denominator. Okay, so this guy doesn't affect the softmax probabilities. It just cancels out. It means that it's enough to look at the other terms here. What are those? It's 2C transpose F minus C transpose C. Rename 2C to be W. It's just renaming. Rename C transpose C to be your B. And what you end up with is a linear layer on top of your neural network. And you're going to have a different weight per each class. This is exactly the setup that we had when we were doing classification. This is the last layer of your neural network, usually. You featureize, the last layer is a linear layer. But now this W, they are not parameters on their own. They are actually being computed out of your own neural network. That's the only difference. So is this clear? So this is basically very related to the type of classification that we are used to. And that's why it is working. There is math behind it. The math is simple. but there is math behind it. There is this data set that I want you guys to explore. It's a small data set, so it shouldn't be that hard to explore it. It's mini ImageNet. You have 6,000 images. You have 100 classes. You have 600 examples per each class. They have low resolution. And what are we doing? The setup is different. Now, this is few-shot learning. You divide your training, validation, and testing based on the labels, not based on your images. Based on the labels, 64 of them are going to give you your training data. 16 labels are going to give you your validation, and the rest of them are going to give you your test classes. That's why during testing, you have new classes that you haven't seen while training. And then you can do few-shot classification on that. And this is prototypical networks, giving you the best results. Model agnostic meta learning. We cover it in reinforcement learning. I have a few slides on that. And the rest of them are the matching network that we covered in the previous slide. Okay.